In the past, I did 2 proofs of Heron's formula. I did the common one, the proof using Pythagoras' law with a lot of algebra. This is the one everyone knows or everyone's worked through. And then I did the one with incircles and excircles and similar triangles. Now, this is a pure geometry sort of proof, this one. And it's a very beautiful proof. So I did a video on that too. I did this in 2 videos, so I will put the links to these videos in the description box. And today I'm going to talk about another proof of Heron's formula, a proof that I wanted to do for a long time. I wanted to get around to this. And this is the proof using the so-called triple cotangent identity. This is a trig identity, and it has a marvelous application to Heron's formula. Now, I think that this here is the most interesting proof that I have yet seen for Heron's formula. Why is it the most interesting? Well, it's because all of the mess, the algebra here, all of this stuff is packed into one trig identity. And it's a really amazing identity. It's easy to remember, easy to write down, and all of that is in this identity. So if you start with this identity, the proof for Heron's formula becomes extremely elegant and free of a lot of algebraic mess. It's much easier, I think, to understand this proof than it is to follow all this algebra here or follow the logic of all this geometry in the incircle, excircle proof, however beautiful all of that may be. So I think this is very interesting because we're kind of like offloaded all the complexity of proving Heron's formula into one trig identity. So we're going to prove this trig identity first, and then we will apply it to Heron's formula. Let's start by proving something called the triple tangent identity. It's very similar to our end result, the triple cotangent identity, but this is quite easy to prove. Start with a triangle ABC. And for this, I will restrict myself to talking about triangles that are not right triangles because I will be doing tangents of all these angles and I don't want the tangent to blow up. It doesn't really limit us because you will see later why. Okay, so the angles here of this triangle add up to 180 degrees, like so. So when this is true, if we have this condition that 3 angles are the angles of a triangle, they add up to 180, then we have the triple tangent identity. And that's tan alpha plus tan beta plus tan gamma equals tan alpha times tan beta times tan gamma. Wow. Well, there are those who say that trigonometry isn't fun. They don't like it. Well, maybe you should show them this here triple tan identity. I mean, this is really beautiful. This really satisfies those aesthetic sensibilities that we have. What a beautiful formula. All right, let's prove this. So I start with this formula and I isolate alpha here. And now I take the tan of both sides. Okay, and now I need to make some room. Okay, let's think about this. So tangent of theta, that's y divided by x. So let's see what happens if we subtract that theta from pi. Okay, well, this here is pi minus theta. So this is the same theta here, except now this is positive y, but this is negative x. So tan theta, pi minus theta, this is equal to minus y over x. Okay, so we have tan pi minus theta equals tan theta. Oh, very nice. Minus tan theta. Hang on. Okay. Well, we can apply that to this step here. And we get minus tan beta plus gamma. Okay, well, that's the sum of angles. So there's an addition rule for tan that I can use here. And the addition rule goes like this. I'm sure you've seen this before. This one is a well-known trig identity. So let's apply that here to this step here. And we get this. But this denominator, well, I can bring it up here, multiply both sides by this denominator, and what do we get now? Well, there we have it, very close to the final result. So let's just rearrange some of these terms. And there we have it, the triple tan identity. I just need to remember, though, that alpha plus beta plus gamma is pi. So these are angles of a triangle. Very beautiful identity and not difficult to prove and easy to remember. So from this follows the cotangent, triple cotangent identity. Now suppose we have a different set of angles. Alpha prime, beta prime, gamma prime with the following condition, that they all add up to pi over 2. So it's not pi anymore. They don't add up to pi like alpha, beta, gamma. They add up to pi over 2. All right, so let's look at something here. Take pi over 2 minus alpha prime, and then I repeat this kind of term for the other angles. Right, so what does this work out to? Well, 3 pi over 2, I add up the pi's. And then I have minus alpha prime plus beta prime plus gamma prime. But that, this here is equal to pi over 2. So if I work this out, I get 3 pi over 2 minus pi over 2, and that's pi. So then these behave just like the angles alpha, beta, and gamma from the previous part, where I talked about triple tangent identity. So I can apply the triple tangent identity. I just have a caveat. The alpha prime, beta prime, gamma prime cannot be 0. They can't be 0 because if there's 0, then I will end up with a tangent of pi over 2, and that's going to blow up. So in fact, this is fine because for the proof of Heron's formula, these angles, as we will construct them later, they will not be 0 anyway, so we don't have to worry about that. And so when I put these angles into the triple tan identity, I get this terrifying expression here. But it's really not that scary because it's very symmetrical and very beautiful. So it's actually very easy to write this down. Let's look at a typical right triangle. This angle here has to be pi over 2 minus theta. So now let's look at the relationship between tan and cotan. Tan pi over 2 minus theta, that's opposite over adjacent. But now let's calculate the cotan of theta. The cotan of theta is adjacent over opposite. Well, that's the same thing here. That's x over y. So they are the same. So I get this pretty little property here, and I can use this property to simplify this terrifying expression up here. And there we have it. This is our beautiful, beautiful cotangent, triple cotangent identity with the following conditions. They see angles alpha prime, beta prime, gamma prime sum up to pi over 2, and none of them are 0 because we don't want cotan to blow up. But in practice, this does not limit us because for all the triangles that we want to find the area of, we're never going to have a situation where one of these alpha prime, beta prime angles are going to be 0, as you will see soon. So now let's look at some applications of this beautiful cotangent, triple cotangent identity. The first application is an application to a triangle with an incircle, and we will get a kind of corollary or a new form of the triple tangent identity specific to this situation. Here we have a triangle with an incircle. So the incircle is tangent at 3 points here. This point, this point, and this point. This is always possible. You can always construct an incircle like this. Now I want to know the lengths of these segments. So let's say this segment here, I will call this segment X. By symmetry, this bit here from A to the tangent point, this must also be X by symmetry of the tangents to a circle. That's a fundamental theorem. Likewise, let's call this piece here from B to the tangent point, and by symmetry of the tangents, again, look, there's tangent point here, this must also be Y along here, like this. Finally, let's call this segment Z from C until the tangent point here, and by symmetry, this segment here must also be Z, like so. Now, the lengths of the sides are A, B, and C, so we have right away that the side C is X plus Y, side B is X plus Z, and side A is Y plus Z. We know that. And we can add up all of this segment lengths, and we get this. Okay, let's divide out the two, and we get this. So we're adding up only half of the perimeter, this X, this Y here, and this Z here. That's all we need. The others are equal. Okay, this, we'll give it a special name, call it P. I know there are people in the audience, some viewers who don't like P for semi-perimeter, but I'm going to do it anyway. I'm sorry. Perimeter, semi-perimeter, I call it P, and that's the way it's going to be. Right, let's solve for X in this formula here. So X is semi-perimeter minus Y plus Z. Okay, so look carefully. What's Y plus Z? Y plus Z is here. So this is A, so X is P minus A. We can continue this. So let's solve for Y. Y is P minus X plus Z. So we're solving it using this formula here. Okay. This formula here. Okay. And what's X plus Z? X plus Z. X plus Z is side B. So that's P minus B. And finally, Z is P minus X plus Y. And what's X plus Y? Well, it must be C here. So that's P minus C. So I have all of these lengths. Let me clean this figure up a bit. There, that looks better. Okay, so X, this is P minus A. And it's easy to remember. You see, this matches with the vertex A. So here you can even guess what it's going to be. It's going to be P minus C, this length, and here P minus B. So I have fully figured out all of these segments in terms of the these pieces that go in terms of the sides of the triangle. So this is all known if you know the sides of the triangle, which we do when we're applying Heron's formula. Okay, so let's make a bit more room and start this reasoning all over again. So here I have my triangle, and I labeled the lengths of those segments. And here is R, which is little r, the radius of my incircle. And notice that these angles are 90 degrees because of the tangency. So if this is angle alpha, then this angle here is alpha by 2, and this angle here is beta by 2. And likewise, this angle here is gamma by 2. And now I can compute the cotangents of these angles. And notice that the following. Alpha plus beta plus gamma is pi, but alpha by 2 plus beta by 2 plus gamma by 2, this is pi over 2. So not only do I get the cotangents now because I know all these lengths, I can apply the triple cotangent identity because I have this condition here that they add up to pi over 2. So what is cotangent alpha by 2? Well, cotangent is, let's think about this. It's adjacent over opposite. And opposite is r, so that's p minus a over r. Cotangent beta over 2, easy to figure this out. Beta over 2, adjacent over opposite. Opposite is going to be r, p minus b over r. Cotangent gamma, gamma over 2, this is adjacent over opposite. So adjacent over opposite, and that's p minus c over r. So here is my triple cotan identity. Alpha prime is this, beta prime is this, gamma prime is this. They add up to the right thing. And what do I get? Well, I plug everything in. And I get this beautiful corollary to the tangent, triple cotangent identity. This is actually just the triple cotangent identity all over again. It's just phrased in terms of the sides of triangles rather than using the word cotan. And this is what we need to prove Heron's formula. So this is where all the complex algebra lies underneath in here. So if you know this thing, which is kind of really easy to deduce from looking at a triangle with its incircle, that was not hard at all. We just used the triple cotan identity and it came just naturally. So if you know this, then everything that follows in the proof of Heron's formula is really elegant now, and you will see what I mean. And now we're ready for Heron's formula. Here's my handy incircle diagram again, and I've labeled all the segments, and I labeled these radii, the radius of the incircle. Now, if I look at this carefully, I can decompose the area of my big triangle into smaller ones. And by abusive notation, I'll call the area of the big triangle capital A. And we can see here that we can add this triangle. Well, what is the area of that triangle? Well, it's 1/2 times the radius times the base, p minus a. Okay, but I have two of these exact same ones, and so that's 2 times this. Right, so I can continue with the other ones. And I get that. Okay, and I simplify all of this, and what do I get? The 2's cancel out, and I get this. Well, if I take out another factor of r here, so I'll end up with r. Well, what does that look like? Well, that looks like my cotangent, triple cotangent identity corollary. And so let's apply the corollary now. Let's apply, well, it's just a different form of triple cotangent identity. So let's apply that here. And I get this, and I can do some simplifications here. I can take out this like that. Let me write that better. There, that's what I have. Right, so I'm almost there. I just have this problem of r. What is r? I have to eliminate this, so I want to eliminate r. And it turns out it's very easy to do. You can just apply this formula that everyone knows. The area of a triangle is r times semiperimeter, where r is the radius of the incircle. But let's prove this anyway and see how it goes. So we'll go back to this formula here. Okay. And if we simplify this formula up here, we get this expression over here. And a little bit more algebra. Let's look at what happens here. P minus A plus B plus C. This is 3P, sorry. There's one P here, one P here, and one P here. Yeah, 3 of them. But this here is 1P also. This is actually 2 semi-perimeters. Okay, so this is R times 3P minus 2P. Okay, it's a case against me using P, I guess. All right, so this is R times P, a beautiful formula. And okay, we solved for R now. R is A over P. So I have here P over A times P minus A, P minus B, P minus C, like so. Okay. And so now I take this A and bring it over to the other side, and I get the following. And there you go. This is Heron's formula, or if you like, you can write it a different way, like this. And I think this is a beautiful proof. It's very rich. It's full of interesting ideas, really novel, cool concepts. And I like especially how much of the complex algebra is just packed away into that cotangent thing. So if you like this, click like, comment, and subscribe. Tell me what you think of this cotangent proof. And I will see you next time.